So harmonic motion is a key application of this thing, that why we switch to t and stuff. They're stating like this: y equals a times the sine of, we've seen this one before, a times sine of, and instead of using k, they're using Greek letter omega and t. Remember the problem where boys are spinning the stone a while back? And there we use omega. Anybody remember what this omega is standing for? Angular speed, right? Angular speed. Now, this is a mass attached to spring is going up and down like this, but what is the secret of this motion? There is actually this angel spinning in this stone, and shadow image is actually this one, right? So in describing this motion, we use like this, but in a higher dimensional thinking, and there is actually something circular motion, that angular speed is involved. So you will see this a lot in physics. Although there is no circular motion, they are still using this term, an angular speed or angular momentum. That's the word they use, is because of this connection. All right. So it's going up and down, and it's going to use model this one. Hooke's principle, differential equation, leads you to the mathematical conclusion it must be in this form. All right. That's the connection. It's called simple harmonic motion. The book also introduces a damped harmonic motion, but we're not going to do damped harmonic motion. It's not important for calculus. You will definitely learn it very carefully, nicely in a differential equation. So this is already just a different letter. So what's involved in here, and graphs and terms, and exactly the same. Amplitude, no problem. You all know what that is, right? Amplitude of this graph. That. Period, 2 pi k, right? 2 pi divided by k. Here they're just simply using a different letter, omega, angular momentum. Okay. How about frequency? Anybody remember the relationship between period and frequency? If you have a period, how do you calculate frequency? So right, reciprocal. You see that? 2 pi omega, omega 2 pi. Right? But if it is moving really quick, frequency is a better magnitude to deal with than 0.002 as a period. So back and forth. If it is slow, they will describe with the period. If it is fast, they're going to describe it with the frequency. All right. So they begin to actually show you the actual example, such as this one, and let me just show you that example in here. Vibration of spring, then 10 times the sine of 4 pi t. 4 pi there is omega, right? That's angular momentum. And you know how to calculate amplitude and period and frequency. No problem, right? You all know that. So I'm just going to look at an example. They didn't give you the graph, the function, and you're supposed to figure it out. And that's what this problem is about. And that's going to be the last thing today. All right, there's no function given. They're describing the motion, right? When we look at this, always think about, there is my equilibrium position. And sometimes they trick you with the equilibrium position. Equilibrium position is not 0, but it's somewhere above. It's not a big deal. But here is an equilibrium position is 0. So here's the thing. So a mass is suspended from a spring, just like that situation above. Spring is compressed. Distance 4 centimeter. Compressed to here. If it is attached to here, I think you're rising in it. So initial position is over here. Is that okay? Then released. Then what's going to happen? This one will go down and hit the lowest point and come back up. Isn't that the expected motion? Right? Compress the spring, release it, go down, and come back up. That's the motion. It looks like what kind of curve? Here, as time goes, is expanded velocity is going down, hit the lowest point, and coming back up. Is that okay? What curve? Cosine curve. Reflected or not? No reflection. Okay. What else do you see as you further reading? Okay. It is observed that, what about 4 centimeter? What are you going to do about that distance of 4 centimeter? Right. That is a 4 centimeter here, right? So what is A? Amplitude for it. Amplitude here is 4, and A value here is positive 4 or negative 4? Positive 4, because there's no reflection. So we already know A part there and cosine part, right? All we have to figure out is omega. What else do we know? It is observed that the mass returns to the compressed position after 1/3 second, right? If it came back to the compressed position, is that one cycle? That's one cycle. Let me say this one. If it is start in equilibrium position and rises and come back to the equilibrium position for the first time, is this one cycle? No, this is not one cycle. Yeah. You have to go below and come back up to the original position. That's one cycle. So don't get tricked by this one, right? Or you started here and reach the bottom within 1/3 second. Is that one cycle? No, it's not. We only need the half cycle, right? You have to come back up. So don't get tricked by this type of thing. Make sure you understand it's a complete one cycle. Especially if it starts in an equilibrium position, that can be confusing. You go up, and go down, come back up. This is one cycle. All right? But this is definitely one cycle, right? So what is this 1/3 is called? Time it required for one cycle. Period. So we already know the period from the description, not from the graph, but from the description. But how is this period is connected with omega? All we have to figure out is A and omega, right? There's no equilibrium position shift. This is it. So this is the connection. How is this period is connect? How is omega is connected to period? Two pi divided by omega, right? And that should be 1/3. That's the connection you have to make. 1/3 is given, but it is connected to omega in this way. So what is omega? 6 pi. We got A and we got 6 pi. So how does the motion look like? Y equals 4 times cosine 6 pi t. If you sketch that, and it's gonna, and then you just, I think that's it. Function is this, and you can sketch it. You practiced it a lot last time. Yeah. All right. You never know what happened when I sit in front of a computer and begin to write. This is where I ended. And it's 3:15. And it's time to forget everything. And then